Imagine you're trying to build a whole thriving city from scratch, but the absolute closest hardware store is literally 140 million miles away. Well, that's exactly the reality we face when we talk about a future Mars colony. In this explainer, we're diving into a newly published paper by researchers Serena Soriano, Shamil Bikdemirov, Dmitry Pertikin, and Anton Ivanov. It's called Asteroid Mining to Sustain a Mars Colony, a Logistics Point of View. And what they've mathematically proven here is that an interplanetary supply chain isn't just a sci-fi dream anymore, it's actually possible, and we can model it right now. So, why does this matter right now? Well, we call this the heavy metal problem. If we're going to build sustainable habitats, repair rovers, or construct any real infrastructure on Mars, we need massive, and I mean massive, amounts of iron and metal. The issue? Launching heavy steel all the way up and out of Earth's deep gravity well is insanely expensive. It's totally inefficient, and frankly, it just doesn't scale. If we want a permanent, thriving colony, we absolutely have to find a local, off-world source of heavy metal. Okay, let's dive right into this. The researchers' initial approach here was pretty brilliant, yet surprisingly simple. Instead of looking backward toward Earth for their building supplies, they looked up. They mapped out a potential supply chain routing from Mars straight to near-Earth and main belt asteroids. The main goal? Hunt down metal-rich space rocks, what we call X-type metallic asteroids that orbit relatively close to Mars, mine them, and then bring all that precious metal right back home to the red planet. But of course, strict physics always gets in the way. If you're modeling this on modern heavy lift rockets, kind of like SpaceX's Starship specs, you are dealing with a very rigid fuel budget in deep space. We measure this in delta V, which is basically the change in velocity. And this theoretical cargo spacecraft, it maxes out at a delta V of 6.4 kilometers per second. That is your absolute hard mathematical limit for any single leg of the trip. Think of it exactly like your car's gas tank. Once you hit zero, that's it, you're stranded. And, that strict limit creates a massive roadblock for this whole idea. We definitely have enough fuel to launch from Mars and reach one of these metallic asteroids, no problem there. But once we load the ship up with 115 tons of freshly mined heavy metal, the spacecraft becomes far too heavy. We literally cannot carry that payload back home with the fuel we'd have left in the tank. It completely breaks the fuel budget. So, the team ran the numbers. Out of the thousands and thousands of known space rocks out there, they mathematically filtered the data down to the metallic asteroids we can actually reach from Mars without breaking that 6.4 kilometers per second fuel limit. The result? They found exactly 122 viable targets. Which sounds great, right? But again, you can reach all 122 of them, but you can't get home from a single one. So how do we actually solve that? Now, what's really interesting is the genius twist the researchers introduced. Carbonaceous asteroids. These are known as C-type asteroids, and they are essentially giant, flying, water-rich rocks. The team realized that by making a slight detour to one of these on the way back, we can actually use them as cosmic gas stations. We could process their water into rocket propellant right there in deep space. To see if this would actually work, they systematically tried to pair up those 122 metallic asteroids with nearby carbonaceous ones. They tested the exact orbital trajectories and calculated the fuel costs for every combo. And after throwing out hundreds of combinations that just required way too much fuel, they found exactly 22 perfect pairs. That's 22 instances where a metallic rock and a water-rich rock orbit closely enough to make the interplanetary math perfectly align. So what does this all mean for us? It leaves us with an incredibly elegant three-step blueprint. Step 1, we launch an empty cargo ship from Mars to go mine a metallic asteroid. Step 2, we take a short, low-fuel hop over to its paired carbonaceous asteroid to mine water and manufacture our return fuel. And finally, Step 3, we fly back to Mars, completely fully fueled and loaded down with heavy metal. It's a workaround that perfectly skirts the fuel roadblock without needing any magical, futuristic tech. And this brilliantly illustrates just how deep the research goes. For a specific metallic asteroid named 332 Siri, the team ran these massive genetic algorithm simulations to map out the optimal launch windows. We're talking about a 20-year schedule starting in the year 2040. They literally pinpointed the exact days when the planetary alignments would require the absolute minimum amount of fuel to make these hops. The rigor here is just incredible. This represents a massive paradigm shift. You see, the traditional idea for an Earth supply chain relies on fighting our massive gravity well. That's incredibly costly, and it severely limits how fast a colony could grow. But this proposed asteroid supply chain, it relies on lower gravity, off-world hopping, and what are essentially infinite resources. It creates a completely self-sustaining loop that is totally independent of Earth. Now, to be totally fair, there are definitely still some unknowns in this blueprint. We know the orbital math works flawlessly, but we do still have to physically invent and test the zero-gravity mining drills and the deep space fuel factories. And depending on the specific asteroid, the actual daily mining rates could vary heavily, anywhere from 100 to 800 kilograms a day, which would obviously alter the timeline a bit. But honestly, despite those engineering hurdles, the fundamental physics are incredibly sound. This paper takes the idea of asteroid mining completely out of the realm of science fiction and turns it into a mathematically proven, scheduled blueprint. The roadmap to a thriving city on Mars might just be paved with asteroid metal. So the only real question left is, when do we start building the gas stations?